This is Unit 2, Section 1. We are going to be talking about quadratic functions, and this is textbook section 2.2. So a quadratic function is a function where the highest power is 2. And here we see a quadratic function in standard form, y equals ax squared plus bx plus c. And the quadratic function is represented by a parabola on the coordinate plane. All right, parabolas look like a U shape. There are some key features to parabolas. So just like every other function, we could talk about its domain and range. All right, domain is always going to end up being all real numbers, and then range is the output. There are x-intercepts to a graph. There is a y-intercept to the graph, right? Anywhere it crosses are those intercepts. There are increasing and decreasing intervals, and we'll talk a little bit more about what it means to be an increasing and decreasing interval. There's something called the axis of symmetry, right? Axis of symmetry we didn't draw on here, but would look something like this. And then there's the vertex, right? That would be the vertex. So going more into depth into each of these terms, the vertex is the point where the graph changes direction. It's also going to represent the maximum or minimum of the graph. So if it's the highest point, it's the maximum. If it's the lowest point, it's the minimum. The axis of symmetry is the vertical line through the vertex that splits the graph symmetrically, right? Axis of symmetry, symmetrically. The x-intercepts are where the graph crosses the x-axis. It's also considered the solutions of the quadratic or the values of the function when y is 0. Our quadratic can have two x-intercepts, one x-intercept, or no x-intercepts. The y-intercept is where the graph crosses the y-axis. This is often the starting position in a word problem. Right? The y-intercept is the value when x is 0, therefore it's when time is 0 if x represents time. The decreasing interval is the side of the graph, or the side of the vertex, or the side of the axis of symmetry that is decreasing when going from left to right. So if I had a graph that looked like an upright parabola, it's decreasing until it reaches the vertex, and then after the vertex it starts to increase, and then that would be the increasing interval. If it opened down, then it would be increasing before the vertex, and then it would start to decrease after the vertex. Domain, again, we said was all possible inputs, and range are all possible outputs. For a quadratic, the range will always end up being less than or equal to or greater than or equal to the vertex value. So for a maximum value, we're going to have y is less than or equal to a number. And for a minimum value, we're always going to have y is greater than or equal to a number. So in this example, we're going to identify some of those key features: the domain, the range, the x-intercepts, the y-intercept, the axis of symmetry, the vertex, the maximum minimum value, and its increasing and decreasing intervals. So let's start with the domain, right? Domain, we said, is going to be all real numbers. Make that look more like a D. The range, right down here is our lowest point. So everything that's the range is going to be above that, greater than or equal to, and the y value there was -3. Right? The x-intercepts are the places where it crosses the x-axis. So I see my graph crosses the x-axis here, and it crosses the x-axis here. So we have one intercept at 1, 0, and we have another x-intercept at 3, 0. The y-intercept is where it crosses the y-axis. We see that it crosses the y-axis up here at 0, 9. The axis of symmetry is exactly in the middle, and the axis of symmetry, I'm going to write it as AOS, is always an equation. So it's x equals, and it's whatever the x value was through all of these points, which was 2. The vertex. The vertex is the point where it changes. So notice it was changing down, 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 got to here, and started going up again. So this point is the vertex, and that's at 2, -3. Since there's the bottom right? That vertex is the lowest point. It's a minimum. So the minimum value is negative 3 when x equals 2. So the minimum value is negative 3, and it occurred when x equaled 2, and then increasing and decreasing. So I know it starts by decreasing. So decreasing when x is less than 2, right? That's where it changed at 2. And then after 2, it started to increase. So it's increasing when x is greater than 2. All right, and those are all the key features of this graph. You try this one. Pause it, and I'll show the answers. All right, so my domain is all real numbers. The range is y is greater than or equal to negative 4. My x-intercepts were at 0, 0, and 4, 0. My y-intercept was then also at 0, 0. The axis of symmetry was x equals 2. The vertex was 2, negative 4. That means the minimum value is negative 4 when x is 2. And it was decreasing when it was less than 2, and then increasing when it was greater than 2. Different forms of the quadratic equation are going to give us different key features. So we have three forms we're going to talk about. We have standard form, which is y equals ax squared plus bx plus c. We have intercept form, where it's y equals a times x plus or minus a number times x plus or minus another number. And then vertex form, you'll notice this looks a lot more like what we did with our transformations. Y equals a times x minus h squared plus k. The first form here is standard form. And the standard form can tell us two things automatically. The c value is going to be our y-intercept. So we will always be able to tell the starting position from a standard form equation. The other thing it could tell us is if it opens up like this or down like this. So positive is what makes it open up. Negative is what makes it open down. So just like the reflection, the a value in front always told us if there was a reflection or not, that's going to be true in standard form as well. So this was my standard form equation. We noticed that we could tell, based on this negative 3 here, that the y-intercept should have been at negative 3. And if I look here, my y-intercept is in fact 0, negative 3. In intercept form, it's named as such because it tells us the x-intercepts. So notice this says x minus p and x minus q. So that means p comma 0 and q comma 0 are going to be my x-intercepts. I can also tell if it opens up or down. All right, we'll always be able to tell if it opens up or down, no matter what form we have. So looking at the same function as before, but now written in intercept form, I could tell x minus 1 means I should have had 1 comma 0, and x plus 3 would mean I have negative 3 comma 0. And if I look at my x-intercepts, those are in fact the 2 points. Then we have vertex form. So vertex form, again, will tell us if it opens up or down, but will also tell us the vertex, right? It's named vertex form because it gives us the vertex. The vertex is going to be h, comma, k. So notice it was x minus h, so we're going to take the opposite value of inside, and then plus k, whatever number that was exactly. So looking at this one, I see that my vertex should be opposite of positive 1, and then minus 4. And if I look at my picture, my vertex was negative 1, negative 4. So you notice all three of those graphs were all the exact same graph, but they were each written in a different form, each highlighting a different key feature. So we should be able to take out a piece of key information from each of these functions based on what form they're in. So for A, it's written in vertex form. So I automatically can tell for A that my vertex is opposite of the inside, same as the outside. So my vertex would be 5, 7. In B, this is standard form. So standard form, we look to the C value. I know my y-intercept would be 0, comma, negative 6. And for C, this is an intercept form. So I know my x-intercepts would be 4, comma, 0, right, opposite of negative 4, and then opposite of negative 8, 8, comma, 0. So you try the next three, identify a piece of key information from each one, pause, and I'll show the answer. Okay, so for the first one, we can identify the x-intercepts. For the second one, we can identify the vertex. And for the third, we can identify the y-intercept. I also said before we could tell if a graph opens up or down. So this one would have opened up because 3 is positive. This one would have opened up because the invisible 1 was positive. And this one would have opened down because it was negative. So now we're going to rewrite the function to reveal the y-intercept. So that means I want this to be rewritten into standard form. So if I want this in standard form, I'm going to have to change my x plus 3 squared. So to do that, it's really x plus 3 times x plus 3, and then minus 4. So if you recall how to multiply, right, we're foiling or distributing. We're going to distribute the x twice, so we get x squared plus 3x, and then we're going to distribute the 3 twice. So we get plus 3x plus 9. And I'm going to bring down my minus 4. So this means I can rewrite my equation as x squared plus 6x plus 5. And my y-intercept, I can now tell, is 0, 5. Let's look at the next one together as well. We want to rewrite the function to reveal the vertex. So this is standard form right now, and I want it to be into vertex form. If you recall from Algebra 1, we did something called completing the square. And to complete the square, we focus on the b value, the middle value, and we're going to start by cutting it in half. So half of 10 is 5. So what we're going to do is we're going to complete the square by squaring it. So I'm going to add 5 squared, or 25, but I'm going to take it away right away, minus 25, because these cancel each other out. It's like I'm not changing the equation at all because they cancel each other out. And now I'm going to focus on keeping just this part together. So x squared plus 10x plus 25 is factorable. It factors into x plus 5 squared. And I can combine these to get minus 7, which I now have my function in vertex form. I'm not going to make you guys complete the square. I just wanted to show you that this is possible. We're not there yet in our year, but this is something we can do. So my vertex I can now pull out to be -5, -7. Okay? You're going to try the next one. Rewrite the function to reveal the y-intercept. So we are written in x-intercept form right now. We want the y-intercept, so we need to put it into standard form. So you can pause, try it, and I'll show the answer. All right, so if I multiply, FOIL, distribute, whatever you want to call it up there, and then I also distribute the -2, I end up with a c-value of 6, so my y-intercept is 0, 6. The last thing we're going to talk about today is the average rate of change for a quadratic, which is basically going to be the slope of the line between any 2 points on the quadratic called an interval. So what we do need to know is the rate of change for a quadratic is not constant, right? A linear function is named linear because the rate of change remains constant. But in a quadratic, it depends on which two um, points you choose for your interval, because here and here, I end up with a slope that looks something like this, whereas if I chose here and here, I would end up with a slope that's much more steep. So it changes as the intervals change. But it's still just going to be finding the slope. So we're going to find the average rate of change over the specified interval. So they're telling us from 1 to 4, which means from x is 1 to x is 4. So the two pairs we're looking at are 1, -1 and 4, 14. So if I'm focusing on the slope between 1, -1 and 4, 14, if you recall, slope is found by doing change in y, or y2 minus y1, over the change in x, or x2 minus x1. So we're going to have 14 minus -1 over 4 minus 1. So this becomes 14 plus 1, or 15. This becomes 4 minus 1, or 3. So my average rate of change is 5 over the interval 1 to 4. We could also do it with a graph. So if we want to find the average rate of change over this interval, we're going from -5, which was here, to -1, which was here. So we're looking for the slope, or the average change of this line here. So we're starting at -5, -1, and we're going to -1, 7. So we're going to do the same thing. We're going to find the slope. We have x1, y1. We have x2, y2. So it's 7 minus -1 over -1 minus -5. So that becomes 8 over 4, or 2. The average rate of change there was 2. So you try this last one, pause it, and I'll show the answer. All right, so the average rate of change for that one was 7, and that is our day 1 of quadratics from Unit 2.